In this lesson, we provide some classical functional equations. We start with an encryption equation and we continue with the bisymmetry and associativity and the generalized associativity equations. Since we want the readers to connect these equations with functional networks, we also include some illustrative graphics and expect the reader to enrich from this use of functional equations. Finally, we end with the Cauchy's and the Pexyder's equations. Some examples of application are given. Our first functional equation is an encryption functional equation used to provide security of our bank account. Assume that you want to encrypt a key to access a bank account in which X is the key supplied by the user, Y is a key of the supervisor, and the bank has the possibility to transform the final key by means of a formula F such that the due security is guaranteed. The G, H, and F functions are known only by the client, the supervisor, and the bank respectively. The question we asked ourselves here is about the existence of more than one set of these three functions providing the same result. In other words, we ask about the existence of two pairs of functions, G1, H1, F1, and G2, H2, F2, such that the resulting value coincides for all possible input data X and Y. In addition, if the answer of this question is positive, we are interested in the relations among these functions. The solution of the stated problem is given by this lemma that says that in fact those functions exist and that they are related by the indicated linear relations. Though there is not a unique solution, the existing solutions are related only by linear relations. This lemma is very important to deal with the problem of uniqueness, because some of the resulting solutions of our functional equations will be particular cases of it. Letting U and V be the indicated values in the first line and replacing them into our functional equation, repeated in the second line for convenience, we get the indicated Pexyder's equation, where the asterisk F2, G2, and H2 are the indicated functions. The Pexyder equation 1 will be analyzed later in this lesson and has the solution in equation 5, which replace into expression 4 after some simple manipulations based on the concept of inverse functions lead us to the solutions in. Next, we deal with an important functional equation that states that operating with four inputs, X, Y, U, and V, we get the same result if we operate in two different forms, as indicated by the two right and left-hand sides of the equation 6. Note that we make some assumptions about the invertibility of the involved functions. This theorem provides the general solution of this functional equation. This means that we know what functions satisfy the equations and at the same time that no other function satisfies it. Thus, in real practice, we cannot use other functions if we want the set of indicated conditions to be satisfied. Note also that the initial functional equation depends on 6 functions of 2 arguments, while the solutions depend only on 9 functions of one single argument. This means that the functions are seriously restricted in order to satisfy the functional equation. We will see later that expression 6 will be even more restricted because the F, G, L, and M cancel out when replaced in 6. This is a very relevant result because we can simplify our models if we impose to the appearing functions some restrictions in terms of functional equations. We have added this transparency for the user to understand better the meaning of the functional equation. We have plotted in red color the input data and in blue color the output, so that we can visualize better the plot. The functional equation forces the results of two different processes indicated by the two functional expressions in the figure to deliver the same output. To those working in artificial intelligence, and in particular with neural networks, either regular or deep, we must indicate that our network is much more powerful because we have connected our output with two different arrows to force identity of results. This possibility does not exist in existing neural networks. In this transparency, we deal with the uniqueness problem of the functions involved in the solution and based on our previous lemma. An interesting result to emphasize is that when replacing the solution into the initial functional equation, we get the expression 9 that involves only 5 functions on one argument. As indicated before, the f, g, l, and m functions cancel out. Consequently, our initial expression depending on 6 two-argument functions depends only on 5 one-argument functions, what means a very important complexity reduction. This plot reveals how is the structure of the resulting simplified network. In this figure, we can compare both networks and the associated complexities. This corollary gives the general solution of a particular interesting case of the previous functional equation and the corresponding general solution, together with the uniqueness associated considerations. Since an image worth more than 1,000 words, we include here the network associated with this functional equation. As before, it shows two paths or processes leading to the same output. Note that again two argument functions are involved. Here we repeat the general solution, which depends on 7 k, f, g, p, q, m, and n one-argument functions. In addition, replacing it into the functional equation, we get the simplified equivalent expression, which depends only on 4 one-argument functions. Note that the functions f, m, and n have cancelled out. As before, the initial expression has reduced complexity a lot. The resultant simplified network is shown here, where the complexity reduction can be seen graphically. The proof of the theorem is given here. It is based on our lemma. A careful analysis of this derivation will allow the reader to check that the general solution of the initial functional equation is in fact the one indicated. Finally, this figure allows us to compare both networks in terms of complexity and functions involved. I expect readers working in artificial intelligence to benefit from the relevant ideas reported here. In addition, it will be convenient, in order to facilitate explanation of results, that the variables indicated by all nodes in red, green, and blue colors to be interpretable. Now, I am going to show you a very curious property, that is the associative property. We have used the associative property many times in our life, and it is a very difficult property because it is not easy to obtain a formula to obtain all associative operations. An associative property means the following. I have 3 numbers, 3 real numbers, x, 1, and z. I obtain the same if I operate x first with y, and then the result with z, as if I operate first the y with z, and then I operate the x with the result of x and z. If I call f of xy to x operated with y, then the previous expression, that is the associative property, can be expressed as the functional equation that you have there, which is a functional equation because it's only one equation and has only one unknown, which is the f, capital F, that is the operation. Now we are going to see, and it will be a pleasure for you, how are all associative operations. And functional equations will reveal us the form of these associative operations. F of xy, that is x operated with y, is f minus 1 of fx plus f of y. We were looking for a function of 2 arguments, x and y. And now functional equations tells us that we only need one argument function, the f function. So we have simplified the problem a lot. And that this function has to be invertible. So in this formula, you can see all possible associative operations with real numbers, and there are no more. If a function, if an operation cannot be written in this form, it won't be associative at all. This can be represented graphically, so that you can first calculate f of x. You have a line in blue color that represents the f function. So you enter with x, and then you obtain the f of x. Then you enter with y, and you obtain the f of y. We add fx plus fy, and you obtain another point there. And then you need to enter to calculate f minus 1, the inverse function. So you enter on the other side, and then you obtain down the value of the result. So this is a graphical illustration of all associative operations. If you change the blue line, you get
different associative operations. Of course, this function need to be increasing. But the funny thing is that for the first time probably in your life, you have been able to see all associative operations.
In this transparency, we show how to solve the associativity functional equation as a particular case of a previous functional equations and our lemma. Replacing back and using the solutions of previous functional equations, we obtain the desired result. Once again, we insist in the fact that all associative operations between real numbers must be of this form. For illustrative purposes, we provide two examples. The first is the product, which comes from the logarithmic function f. The second comes from a monomial function. Since we know that any associative operation is associated with a monotone function, we can ask about the uniqueness of this function. In this transparency, we answer this question in the negative sense, but we identified all functions given the same associative operation, which must be related by a constant factor c. Finally, replacing the general solution into the functional equation, we obtain the general formula for operating three input values, x, y, and z, as indicated. The corollary goes even much further because it establishes that the plus operation in the general formula can be replaced by any associative operation. Thus, the important fact is the associative character of the operation used and not in the sum itself. In this transparency, we prove that the sum operation can be in fact replaced by any associative operation. With a little effort, the reader should be able to follow the proof. I recommend this to get the maximum benefit from it. Here, we present an example of application to solve a real problem. Let us assume that we have n quantifiable judgments x1, x2, xn, which we want to synthesize into a consensus judgment, that is, a function f of all the judgments x1, x2, xn. We assume that the consensus function f is separable, that is, it satisfies the condition indicated by the equation in the figure, where we impose some constraint to the operation delta, that is, we force it to be associative, commutative, and cancelable. The associative and commutative property of the operation delta is imposed to avoid any possible type of manipulation of the final judgment. If delta is not associative, the order of the judges can be adequately manipulated to get desired results. Otherwise, the final result is invariant with respect to the evaluation order. The cancelable property ensures that all judges have influence on the consensual result. This theorem implies that delta can be written as in the first expression in the transparency, and then it can be written as in the second expression. We can even add extra conditions to be satisfied by function f, such as unanimity, which is the one in the last line. That means that when all members of the committee assign the same judgment x, the consensus judgment must be x2. If in addition all judges have the same weight, then we will have the condition in the first expression, and finally we will get the final formula for the consensus given in the center part of the transparency. Finally, by choosing different phi functions, we can get different formulas as those indicated, the arithmetic, the geometric, and the LP means respectively. Next, we dedicate some time to the important Cauchy's equations.
Next, I want to write here four very important equations, which are the Cauchy equations. These equations are those that you have there, and the first one is f of x plus y is equal to f of x plus f of y. And then we play with the plus in one side or in the other and change it by a product, and we combining this, we get the four Cauchy equations, which are very well known and which solution is very well known, and you can use it when this equation.
This theorem gives the general solution of the first Cauchy's equation under the indicated condition, which is a constant times x. We know that one example of the Cauchy's equation 1 was already encountered when dealing with the problem of the area of a rectangle. To prove that this is its general solution, first we show that f of n times x is n times f of x by induction, when n is a positive integer. We prove this by induction. It is obviously true for n equal to 1. And if we assume that it is true for n, we show that it is also true for n plus 1. Next, we show that this is true for any positive rational x. Finally, by the assumed continuity of fx, which implies continuity everywhere, we obtain that f of x is c times x for any real x. This theorem provides the general solution for the Cauchy's equation 2. The proof can be seen in this slide, where the first show that f must be non-negative, and later, using a logarithmic transformation, reduce this equation to the previous one to get the indicated solution inside a box. In this example, we derive a model for the survival function of a longitudinal element. Assume a longitudinal element divided into non-overlapping imaginary pieces. Let G be the survival function of the lifetime of a piece of length S, and assume that the strength of all pieces are independent. Then the function G must satisfy the first functional equation in the slide, where the length S is assumed to be divided into two pieces of lengths Y and C respectively. However, this is a family of Cauchy's equation with parameter x, and then its solution constant C must depend on x2, as indicated. Note that we have used the property that says that the survival function of a piece of two independent pieces must be the product of the survival functions of the two pieces. This, together with the Cauchy's equation 2, allow us to find this beautiful model. This theorem provides the general solution of the Cauchy equation 3. The proof can be seen in this slide, where we first make a change of variables using logarithms in order to transform the initial equation into a Cauchy's equation 1, and later, based on its solution, we obtain the desired solution. This theorem provides the general solution for the Cauchy's equation 4. Next, we deal with Pech-Sider's equation, which generalizes the Cauchy's equation.
Pech-Sider generalized these equations using in the second member not the same function but two different functions, g and h. So the first Pech-Sider equation is f of x plus y is equal to g of x plus h of y. And then you can play also with the plus sign and change it with a dot or with the product, and then you get the four Pech-Sider equations, which are very well known, and we know the solution.
This theorem provides the general solution for the Pech-Sider's equation 1. The proof reduces to making x is equal to 0, y equal to 0, and replacing back into the initial equation with the indicated change of function. With this, we get the Cauchy's equation 1 and the looked-for solution. This theorem provides the general solutions for the Pech-Sider's equation 2. As before, the proof reduces to making x equal to 0, y equal to 0, and replacing back into the initial equation with the indicated changes of function. With this, we get the Cauchy's equation 2 and the desired solution. This theorem provides the general solution for the Pech-Sider equation 3. To prove this, we make x equal to 1, y equal to 1, and replace back into the functional equation. This theorem provides the general solutions for the Pech-Sider's equation 4, which include also those in the slide. Setting x equal to 1 and y equal to 1 in the functional equation and replacing back, we get the Cauchy's equation 4 and later the desired solutions. Next, we give a generalization of the Pech-Sider's equation 1 to the n-dimensional case. This theorem gives the general solutions of the indicated functional equation. The proof can be obtained by first letting all x equal to 0 and replacing then into the functional equation to get an equation that can be solved to get the desired solution. Next, we show an example of taxation of functions. Let us assume that two taxes depend on the salary and capital incomes x and y respectively. If we want a married couple to pay the same amount independently of whether it is a separate or joint tax return, we must have the condition stated in the first expression on the slide, where we have initially assumed a different tax function for wife G, husband H, and couples F. This is a Pech-Sider equation 1, and thus the general solution is the one indicated. Finally, if wife and husband, as it must be, have the same treatment, we get A equal to B equal to 0. Next, we generalize the Pech-Sider's equation to the case of vectors and give the general solution by means of this theorem. Next, we present an aggregated allocation model provided by Axel in 1987. A certain amount S of a quantifiable good is to be allocated to n projects. For this purpose, a committee of n assessors is consulted, and the I assessor recommends delivering Xij units of goods to project J in such a manner that it is balanced, that is, adding S units. The problem consists of synthesizing all recommendations into a single aggregate such that the following condition be satisfied. A. The aggregated allocation for the J project depends only on the recommended allocation to that project. That is, B. The total amount allocated to all projects is constant and equal to S. And C. There is a consensus on rejection. That is, when all members decide to provide 0 units to a given project, this is the aggregated decision. The slide explains how a set of substitutions leads to a Peck-Sider equation 1 whose solution is known, and using the B and the consensus on rejection assumption allow us to obtain the solution to our problem. In this lesson, we have seen the most common classical functional equations, among which we have the Cauchy and the Peck-Sider equations. We have seen also the associativity equation and some generalizations that have been applied to solve some artificial intelligence problems. I hope these examples to have motivated you to study and mainly to use functional equations in your work. I invite you to follow the next lesson dedicated to the sum of product functional equations, which allow us to solve very interesting equations such as the normal conditionals families of distributions functional equations.